Hello everyone, and welcome back to another Eng 130 video tutorial. As always, my name is Clayton, and I'll be the one guiding you through this example today. So if you recall last video, we talked about 3D Cartesian vectors and how we've only covered one of the two possible situations you may face in either a lab or a midterm. And that is when we give you either the angles for the vectors to use trigonometry, or we give you the coordinate direction angles so you can solve for the components very directly. However, now we're going to talk about something new, and that's when instead of giving you angles, or I guess you can kind of do angles for this, we deal with coordinate points. Now these points are very, very important because right now, even though it'll look pretty trivial, these are the building blocks towards the hardest part of I guess pre-midterm, before the midterm, because after that part you'll be using this every day. And it's very, very good to know the methodology between this, because we're going to introduce two new things, which I'll get into later, and that's the unit vector and position vectors. And they're basically the same as your force vectors, just a little bit more special. So instead of kind of hinting towards it, I'm just going to get right into the example. So let's begin. Alrighty, so looking at this example, it says it wants us to express each of the forces in Cartesian vector form and determine the magnitude and coordinate direction angles of the resultant force. So this example is basically similar to the last one, with the exception of instead of given like the trigonometry of the vectors, we're going to have to use these points. And if we're ever given these points like this, the best thing to do is use the unit vector, not method, but use unit vectors. But before we go into that, let's just kind of slow down and discuss what a unit vector is. So if we have a force vector, and let's say that the force vector is equal to, let's just put arbitrary numbers, so 2i minus 7j plus, let's say 3k. Let's just say that's our unit vector, and we'll give it newtons. Why not? So this force vector is composed of two things, a magnitude and a direction. So this force vector here is composed of two things. First is the magnitude of the force vector. So that right there is a single number, that it'll be a scalar. It'll have units of, let's say, 10 newtons. It'll have units. And then, of course, there's also a direction associated with this, which we're going to put as u. And that u right there is a unit vector. So what this unit vector is, it's the direction of our force vector. It's not the magnitude, it does not have any units, but it's the direction of the force vector. So for example, if my force vector goes something like this, and it has a magnitude of 250 newtons, what this unit vector is just the direction of this line. It's not the 250, it has no units, it's just the simple direction of this line. And unit vectors are really nice and they're easy to calculate. So let's just erase this here. So what a unit vector, if we just rearrange this formula, we can find that a direction of a unit vector here is going to be equal to the force vector divided by the magnitude of the force vector. So let's just go along with this example for now for fun. So if I'm trying to find the magnitude of this force vector that we already have, the magnitude, we know it's just going to be all three components squared. So it's going to be 2 squared plus 7 squared plus 3 squared. I'm going to put that in brackets. And what happens when we type this into our calculator, hold on, just let me grab my calculator here. So we go square root of 2 squared plus 7 squared. Oops, I'm typing it in wrong. 2 squared plus 7 squared plus 3 squared. What happens is if we get 7.87, and remember, the magnitude of a force vector has units, so this will be newtons. So what this is this is the magnitude of that force vector. So to get the unit vector, we divide the force vector by its magnitude. So we'll have 2i minus 7j, so this is the force vector, plus 3k, and we put in brackets. Remember, the force vector has units. So this has newtons. And we divide that by the magnitude. So that's divided by 7.87 newtons. So this is the formula for a force vector. So one thing that we can see right away here, which is nice, as I said, the unit vector does not have units. It's just a direction. And if we look at this division here, we have newtons on the top, newtons on the bottom. They cross out. So that's why there's no units associated with this. And the next thing you might ask is, Clayton, I have a vector on top, I have a scalar on the bottom. What exactly do I do to divide it? Well, all you do is you take the number on the bottom, so I'm going to just go in this color. What we do is we take this number and we divide each term of that vector by that number. So in the end, we'll still have a vector because it's just each term. So if I'm just going to kind of put this nicely to show you guys, and you guys can do the math to find the exact numbers later, our unit vector is going to be, and I'm just going to put big brackets because it's going to be huge, it's going to be 2 divided by 7.87. So, and this is I, so this is the I component. It's just the 2 divided by the magnitude minus 7 divided by 7.87. Like that. And then this is in the J direction. And then plus, is it plus 3? Yeah, plus 3 divided by 7.87. And this is in the K direction. So that right there is our unit vector. And what you'll find is all of these numbers in the unit vector are going to be less than or equal to 1. And this is a very important property because the reason why it's called a unit vector is because it's a unit. Its magnitude is 1. So this is very important, not for this example, but for the following examples. The magnitude of a unit vector, not just this one, but every single unit vector there is, the magnitude is going to be equal to 1. And that's a very important fact. So if I were to square all these numbers, add them together, and then square root it, finding the magnitude like we did above, you'll get the magnitude as 1. That's a very important fact of the unit vector. So that's how we find the unit vector of a force vector. Now what's nice is, well, it's not nice because it's going to be a lot of work for you guys. I'm going to be honest with you. But what's interesting, I guess, is that if we have 2 points, let's say point A and point B, and we have a force that goes between these 2 points, which is our, let's just say it's F, the one that we solved above. Also along these 2 points is a second vector. And this is very important. This is, if you can understand this concept here, I promise you this will be the hardest concept to understand before the midterm. So pay close attention. There's 2 vectors in this space. There's the force vector. There's a second vector that goes from point A all the way to point B, like this, and it's called a position vector. A position vector. And we denote those vectors as an R. And then we also put a subscript on the bottom to denote which direction it's going. So in this case, it's going from A to B, so our subscript is going to be RAB. Now what's nice about this vector is it follows the same rules as the force vector here. This position vector here, RAB, is made up of 2 things. The first is magnitude RAB, as well as a unit vector. So the magnitude of RAB, that's the length of the vector. And the best way to put it is, let's say I'm standing at A. So let's say I'm a person standing at A. I'm a terrible artist, don't judge. And I took a tape measure. And I put this tape measure, this pink tape measure, from myself all the way to point B. That tape measure is going to read a length. And that length, let's say, is 10 meters. That is the magnitude of that position vector, 10 meters. It's the length of the vector. So if this is 10 meters, that's our magnitude, 10 meters. But here's the interesting part. As we mentioned before, this unit vector has nothing to do with units. It's purely the direction of our vectors. So if we have a unit vector from A to B and our force goes from A to B, the unit vector in this formula down here, I'll highlight it so you guys know, the unit vector in this formula right there, that U, that is the exact same unit vector as this one up here. They're the exact same, which is really nice. Because if our force right here, which is often what we're trying to solve for, our force vector, is equal to the magnitude of the force vector, which we're often given. For example, in this question, those magnitudes are 400 and 250, so they're usually given, times a unit vector. And we can say that that unit vector right here, so the magnitude of a force vector, and that unit vector is the same unit vector here. We can substitute this in, so it's equal to the magnitude of the force times RAB divided by the magnitude of RAB, which is really, really nice. So you can do this in 2 steps or 1 step. The 2-step process, you find the unit vector, and then you can use this formula down here. The second process, which is the 1 step, you can just find the magnitude of the force, the position vector, and the magnitude of the position vector and sub it all into 1. I recommend the first route right here, because let's say you mess up something in this equation and you get it wrong. At least we can check your work here and check your unit vector and hopefully give you some marks. Because you acknowledge that this is the unit vector, we say, okay, they know what they're doing, so we can give them some part marks. So again, I recommend the first one. But if we're looking at this formula here in the end, because this is all we need to solve this question, is this formula right here in the end. Again, I recommend doing in 2 steps. It's how I will solve the coming examples. I'll find the unit vector, but this is just kind of the proof of what we need. So the force vector, like I said, we're usually given. To find the magnitude of RAB, so this bottom one, we need the components of RAB, which come from the RAB vector. So the only real thing that we're missing here is that position vector, RAB. Well, how do we find it? So it's actually a really simple formula. So what happens is you're going to get coordinates. You're going to have a coordinate for A and a coordinate for B, and each coordinate's going to have 3 components, X, Y, and Z. And I'll show you how to find these coordinates in a couple seconds. But let's just say X coordinates are 2, -2, and 6 meters for coordinate A. And coordinate B is, let's say, 4, 1, and -3 meters. If we're doing a position vector from from A to B, all this is going to be RB. So R without the vector sign means it's coordinate points. RB minus RA. So this is important to know, because one of the things that messes up the most students is they look at this term right here, position vector AB, and since A is before B in these subscripts, they think it's RA minus RB, but that is incorrect. What you do is you start with the final point and you subtract its initial point, which makes sense because basically we're ending up at that last point and we would need to subtract any initial point that we started with to get that relative distance. So if these were our coordinate points, what we would have here is we would have what I like to put as 4, 1, -3, and of course as a unit of meters, minus 2, -2, 6 meters. And all this is going to be equal to, so I'm going to put in brackets, because remember this is a vector, we're going to have the squiggle brackets. It's going to be 4 minus 2, which is 2, and this is in the I direction. It's going to be 1 minus -2, so this is going to be +3, so plus 3, and that's in the J direction. And then -3 minus 6, so this is going to be -9 in the K direction. And then we could end the squiggle brackets. And remember that position vectors deal with length. So they have a unit associated with length. So in this example up here, we look at the units. They're in meters. So this position vector would have units of meters. So that would be our position vector. And then again, we can find the magnitude of the position vector, RAB. So the magnitude of it, using the same formula we've always used. So the magnitude is just going to be equal to the x component squared plus the y component squared plus the k component squared. So with all these in the end, we can solve for RAB, sorry, the magnitude of RAB, the position vector RAB, and if we look at our formula, we have everything we need to know to solve this problem. So it works out great in the end. So I know this may be a lot to take in, but let's just go through the problem, and hopefully we can just show you guys it through example and you guys will understand, because I'm not going to sit here and tell you saying, oh, this is so easy, because it's not. This was something I personally struggled a lot with, is trying to figure out position vectors, unit vectors. It's not the easiest thing. So let's go up here and look at our first vector. And let's start off with FAB. So FAB. So right away we know the magnitude of FAB. So if I were to put the magnitude of FAB, that's going to be equal to 250 newtons. It's given right here, 250 newtons. And we know that FAB goes from point A to point B, right there. So what we want to do is find the unit vector from A to B. And the best way to do that is the position vector from A to B. So we want from A to B. So if we're going down here, first thing that we're going to want is the position vector from A to B. So the formula for that is going to be the coordinate points at B minus the coordinate points at A. All right, so now we have to go to the diagram and figure out the coordinate points. So let's start with A. So the coordinate points at A. If we go up to the diagram and we go up here and we go, okay, the vector comes in this direction and it ends up at B. So the first thing we want is the x coordinate points, and that's going to be this distance here. It's going to be from here to here. It's going to be the distance the point is away. Oh, sorry. Yeah, no, that's right. The distance along the x-axis. So this is going to be the x distance here. And sometimes they're nice and we'll just give you those coordinate points. Like FAC, you can kind of see it says the 1 meter, the 2 meter, but sometimes they can be a bit mean and make you solve for it using some trigonometry. But luckily for you guys, as you guys know, it's not that bad. So if we were to go down here, we know that the coordinate point A is going to be 2 times cosine of 40 degrees. And similarly, the coordinate point for the y is going to be 2 times sine of 40. And if you want proof, we just look. So when we're looking at the y, it's going to be the distance along the y-axis. So it's going to be from this point to this point here. So that's going to be our y. And we can solve that using trigonometry. It's going to be 2 times the sine of 40. Now, the last part we need is the z component. So that's how far up the vertical axis our point is. But luckily for us, our point is located at z equals 0. It's on that xy plane. It's not anywhere up high. Like point A, for example, that's somewhere up high. It'll have a z component. However, we're doing the coordinate points at A and I'm starting at B. So I'm just going to erase this, and this is B. I'm sorry for all I've misled. So again, the coordinate point for B is going to be 0. So those are our first coordinate points. The second thing that we can now do is find our coordinate points at A. Ta-da! And then this one's much easier. So I'm going to just erase what I did at B here, so you guys can have a fresh start and see exactly what I'm doing. So we want this point up here. So the first thing we want to do, we want to find out how far along the x-axis it is. But if you look at this point over here, point A is actually on the x-axis. So the x-coordinate for point A is 0. We go up here. Next thing we want to see how far along it is on the y-axis. And since it's actually negative 0.75 meters, for the coordinate point, we have to put negative 0.75. And finally, we want to see how high up it is, so how far up from the z-axis this point is. And we see that it is 3 meters above the axis. So our last point here is going to be 3. Perfect. So now what we can do is we can find position vector RAB, and it's equal to, of course, the squiggles. So I'm going to do each one by itself. So remember, we're going to take the coordinates of B, and subtract the coordinates of A. So for the I direction, it's going to be 2 times cosine of 40 minus the coordinate at A, so minus 0, because the x component of A is 0, and that's the I direction. So then we're going to go plus, and then we're going to put in brackets the coordinate of B, so 2 times sine 40 minus the coordinate at A, the coordinate at A, which is negative 0.75, all in brackets, and this is in the J direction, and then plus, we got the coordinate of B, so this one's 0, minus the coordinate at A, which is 3, and then that's in the K direction. So again, this is a unit vector. We have to enter squiggle brackets, and then we also have to put a unit. So in this case, it is meters. So we type all this into our calculator. You'll find that RAB is going to be equal to, and then squiggle brackets because it's a vector, 1.532I, so 1.532, and that's in the I direction, 2.036, so plus 2.036, and that's in the J direction. And then finally, minus 3, and that's in the K direction. So remember the little hats on top of the letters, squiggle brackets at the end, and of course meters. So we just found basically the hardest part of this vector. So remember I said that even though we have the position vector, we're also going to need its magnitude. So if we're going for the magnitude of RAB, all we're going to do is just square all of its components. So I'm going to go up here, and I'm going to go 1.532 squared, 32 squared, plus 2.036. That's also squared, and then plus 3 squared. And this right here, and what I'll get is 3.936 meters. So 3.936 meters. So now we can just take a step back and let's just figure out what exactly these 4 things mean. And by 4 things, I mean these ones right here. Just let me grab my highlighter. Let's find out what this means, what this means, what this means, and then finally what does the magnitude mean. So let's go up to the question here, and I'm just going to erase some of this because we just found the position vector and its magnitude. So basically this is everything that it means. And let's do this in a pink color so everyone pays real good attention. So the distance from here to here, that distance right there, that's going to be the magnitude. So that right there is the 3.936 meters. So this distance here is 3.936 meters. That's that distance. Similarly, all of these numbers in the position vector, those are the lengths of each component. So let's look at the I. It goes 1.532 along the x-axis. So what that means right here is this distance here from A to B, this is the 1.532. 532, and that's meters. Similarly, for the y direction, we got 2.036. So that means that the distance, good. So that means the distance from A to B, so that would be from here all the way back here. So this distance there, that's going to be the 2.036 meters. And then finally, we have the z, which is negative 3, which of course makes sense because to go from A to B, we have to go down a distance of negative 3. So that's what those are, negative 3 meters. So it does work out really nice in the end because you can see that this position vector is actually just made up of 3 components, similar to a force vector. So hopefully that makes sense because now becomes the fun part. So let's go back to red, and I said that we can do this in 1 step or 2 step. We have all of the stuff we need. So now we can sub it all in to this equation right here at the end and find our answer. But again, I like to recommend this method where we find the unit vector first, because if something were to happen and you guys get something wrong, we can try and give you part marks. Like, I know a lot of you probably by the end of your midterm are going to think that we're mean, but we're not that mean. We're not that mean, trust me. So let's find that position vector, the unit vector u. So as we remember, the position vector u, and this one's from A to B, is going to be equal to the position vector from A to B divided by the magnitude of A to B. Ta-da! So all we do is we take every component in the position vector and divide it by its magnitude. So if I just put squiggle brackets and I'm going to go down because I know I'm not going to have enough room there and it'll just be messy. So it's equal to, I'll put big squiggle brackets. So it's going to be the I component. So 1.532, and that's divided by 3.936. Come on, get nice for me. There we go. That's in the I direction. Then we're going to do the J direction. So we're going to go plus 2.036. That's divided by 3.936. And again, this will be in the J direction. So put our J there. And then finally, we have to add the K component, or the Z component, which is, it's actually minus 3. So I'm just going to go back and I'm going to go 3.936. And this is minus 3 on the top. And this is in the K direction. So one interesting thing too is, remember, the top has a unit of meters and so does the bottom. So they cancel out. So our unit vector here from A to B, it has no units. That's the one thing you got to keep in mind. There's no units at the end. I'm not sure if they'll dock you marks if you do put units, but remember, it just doesn't have units. Just try and avoid it. All right, so now with this, we can go to our force here. And remember the force formula for our force vector, which again is what we're trying to find for force AB. It's equal to the magnitude at force AB, which we know, now times the unit vector AB, which we also now know. So in the end, this is going to be equal to the magnitude of force AB, which is right here. It's the 250 newtons. So I'm going to go 250. And then in the squiggle brackets, I'm going to put that whole unit vector. So I'm just going to divide it with my calculator. So it'll be 0.389i, 0.389i plus 0.517 plus 0.517j, and then minus 0.762k. So again, all we do to multiply this is we take each of those components and we multiply it by 250. So in the end, our force vector is going to look something like this. It's going to be 97.3i, 97.3i, and to get that, all I did was multiply 250 by this 0.389, and then it's going to be plus 129.3 plus 129.3j, so that's our j component. And again, to get this number, I'm taking the 250 and I'm multiplying it by the 0.517. And then finally, we got minus 190.5k. And that's in the Z direction. And that right there is our vector AB, our force vector AB in Cartesian vector notation. And what's nice about this too is all of the components you guys can find are right there. So if the question didn't just ask you for the force vector in Cartesian vector form, and let's say it wants the x component, you can just say that F AB, so force AB, then comma x, so the x component, that's just going to be the 97.3 newtons. And remember, we need units. Even I forget sometimes, but it's a force vector, needs newtons. And then we look at force AB, comma, y. And that's going to be the 129.3 newtons. And then force AB, comma, z is going to be the negative 190.5 newtons. So it's really easy to get the components. And let's say you have the components and you have the magnitude. Well, then you can find the force vector. And that's actually a little bit of a secret, because the best question that they like to throw in the midterms, and I'm not sure if I should tell you guys this, so you want to listen up here, is they love to give you the components of a force vector and then find the position vector, specifically one of the coordinates. And I'll show you an example later on. Don't worry, I'll show you how it's done, but it's a really good question because a lot of students know how to go one way, find the position vector, then find the force vector, but don't really know how to go backwards. So we'll do that later. So the final thing that we need to do, of course, since we just found our answer, is we need to state it and box it up all pretty. So we got force AB, and this is in Cartesian vector notation, it's going to be equal to, and we're going to do their squiggle brackets, 97.3 I plus 129.3 J minus 190.5 K. And again, it's a force vector. We need to throw in the units. And since it's our final answer for this part of the question, we're just going to put a nice box around it. So we say, hey, marker, this is what I want marked. Because a lot of you guys can be real tricky sometimes and try and fool us. Alrighty. So that's the first part. The second one involves the exact same stuff, but it's a little bit easier because it doesn't have this triangle at the bottom with the 40 degrees. So I'm just going to erase some stuff here. Give us a nice new sheet to work with. Alrighty, so now let's do our second force, and red's kind of boring now. Let's move into something more fun. What do you think is fun, guys? I never explored this area. Ooh. Let's go with this. It looks interesting. Alrighty, so let's do force AC. So right off the bat, we know that the magnitude of FAC is going to be equal to 400 newtons. It's just given to us right then and there, 400 newtons. So like the last question, we have 2 points. We have point A and we have point C. And in the end, we're going to have to find that unit vector from the position vectors, and then we can find the force AC. What's nice is we already found coordinate A, which is right here. So I'm just going to copy that down here real quick because we're going to need it. So for A, its coordinates are 0, comma, negative 0.75, comma, 3. And then that's in meters. However, we're going to have to find coordinate C. But like I said, coordinate C is a little bit easier than the other ones. So first thing we want to do, how far along the x-axis is it? So if we go this way right here, along the x-axis, we find that it's 2 meters along the x-axis. So I'm just going to put 2, and then I'll go comma. Next part, we want to find how far it is along the y-axis. And like A itself, it actually is behind it's in the negative zone, so it's -1. So we got -1. And then it's also similar to B, point B, where it's in the xy plane. So the z coordinate is 0. And then it's a coordinate, so we have to put its units, meters. All right, so this is a little bit easier. So we can go R, we want the position vector from A to C. So remember, it's not coordinate A minus coordinate C. It's the opposite. It's our final coordinate. So RC minus RA. I'm actually really liking this color. I have to use it for future ones. Now, but back to the point. So this is going to be in the squiggle bracket. It's going to be brackets, and we're going to have 2 minus 0 in the I direction, plus, we're going to have -1 minus -0.75, and that's in the J direction. And then plus, we're going to have 0 minus 3, and that's going to be in the K direction. And then we end the squiggle bracket, and remember, it needs its units because it's a position vector. Position vectors have a unit of length. So we do all the fancy-pantsy math on this. We're going to get that the position vector is equal to 2i minus 0.25j minus 3k. Minus 3k. Perfect. So remember, now that we have the position vector, to find the unit vector, we need to divide this vector by its magnitude. So the next part is finding that magnitude of RAC. And that's going to be equal to the square root. And it's going to be 2 squared. 2 squared plus 0.25 squared plus 3 squared. I'm just going to finish off the top of that square root sign. And what we'll find is that the vector is equal to 3.614 meters. So 3.614 meters. So that's nice enough. And just again to remember, guys, the magnitude is always just a single number. It's 3.614 meters. And if you guys are remembering what that is the exact length from point A to point C if we were to follow this line, the shortest possible length. That's going to be the 3.614 meters. So that's what it is. And a lot of the times it confuses students. I think there was a problem one year where instead of giving you coordinate points, I forget what it did, but the question actually said the distance between A and C is, let's say, 4 meters. And a lot of students didn't know what to do with that because they just said the distance between. But if they say the distance between or the length between, that means that its magnitude is that number. So if it said it's the distance between A and C is 4 meters, then you know that the distance between those 2 points is 4 meters. Alrighty, so now with this we can start finding our unit vector. So we know that the unit vector from A to C is going to be equal to, and we're going to do our nice big squiggle brackets. So it's nice to show the work even though you can easily throw it in the calculator, but we're going to have 3.614 on the bottom, 614, and this is 2 on the top because that's the x component. That's in the I direction. And then minus 0.25 all divided by the 3.614, and that's in the J direction. And finally minus, and then 3.614 on the bottom, and this top one's going to be 3, and that's in the K direction. So end the squiggle brackets because it's a vector. And remember, unit vectors do not have a unit at the end. Even though it's kind of weird, it's a unit vector, but it has no units. Kind of counterintuitive. But the reason why it's a unit vector, again, in case you guys forget, is the magnitude of this is 0. So if I were to take all of these components, square them, add them together, and then square root that, so the typical formula like you see above right here, you'll find that its magnitude is 1. And again, not important for this example, but there will be examples later on where it'll make your life a heck of a lot easier. So just stay tuned for that. I think it's towards the end of this week. Alrighty, so if we sub all these numbers in, so why not? You guys probably want to know exactly what they are. For those of you who are hopefully following along at home or in the dorms at Lister. Oh, Lister. 0.553i minus 0.069j minus 0.830, 0.830, and that's in the K. And again, no units. So now we can find FAC now. Getting that. I'm going behind. All right, FAC, because that's equal to the magnitude of FAC times the unit vector from A to C. So in the end, this is going to be, we look at the magnitude, we just scroll up. FAC 400 newtons. So I'm just going to put 400 here. And then I'm going to put my vector 0.553. And that's in the I, minus 0.069 in the J, minus 0.83 in the K. Perfect. So in the end, we'll get the vector that goes like this. It's going to be 221.3 I, 221.3, and that's I. So again, this is just me taking the 400 and multiplying it by the 0.553. And you're going to get minus 27.7, so minus 27.7 J. So this is me taking the 400 and then multiplying it over by the negative 0.069. And to finish it off, it's going to be minus 332, minus 332.0, and that's in the K direction. So another thing too, this is a force vector. It has units, so our units here are newtons. And just to put on the side so everybody knows, this is FAC. So remember, if you wanted the, let's say the Y component of FAC, that's just going to be the negative 27.7 newtons. That's how much of the Y component there is. So that's what's really nice about this method. So to finally finish it off, since this is part of what they're asking in the actual question, we should state our answers. So I'm just going to go down a bit. Actually, this is neat enough. So this is our answer. I'll put a nice box around it. Oh yeah, beautiful. Perfect. Alrighty, so now we have our two vectors using position vectors and unit vectors. But we're not done yet because it also has to determine the magnitude of the resultant force and its coordinate direction angles. So if you guys remember from last video, this is going to be the easiest part for you guys because it's just substituting into a formula. And you guys are all really smart, and I trust that every single one of you knows how to substitute numbers into a formula. But before we do that, we have to find that resultant force. So remember that the resultant force, F, and that's going to be, the resultant force is going to be FAC, or FAB first, it doesn't matter which one, plus FAB. So I did AC plus AB, it does not matter which one. So I'm just going to put in squiggle brackets here because I'm going to write everything out to make it very clear what I do. So I'm going to take the x component of FAB, so 97.3 right here. It's going to be 97.3. And then I'm going to add the x component of the second one, which is 221.3. 221.3. So that's going to be the coordinate in the I direction. I'm going to plus the stuff for the j. So I look up here, we got 129.3 J, so we're going to go 129.3, 129.3, and then we're going to add the negative 27.7, so I'm just going to go in brackets, negative 27.7, and that's going to be in the J direction. And we're going to finish it off here with the K direction, so plus, and we'll go to the top, negative 190.5, so I'm going to go in brackets, negative 190.5, and then subtract the J from this side, which is negative 332.0, and this right there is in the K direction. So then we can end the bracket, and of course it's going to have a value of newtons. And once you do all the math in there, you'll find out that this vector is equal to the following. 318.7 I, 318.7 I, then plus 101.6, so plus 101.6 0.6, and that's j, minus 552.6, and that's in the k direction. And that's also has a unit of newtons. Sorry, I made a mistake here. This is actually a plus because they're not coordinate points, so it's going to be plus. Alright. So finally, now that we know the vector FR, we can use its components to find its magnitude. So we know that the magnitude of FR is going to be equal to, and we're going to square root all of the components. So we're going to go 318.7, 318.7, and that's going to be squared, plus 101.6, also squared, plus 552.6, also squared. And we're going to drag this along. Perfect. And what happens is we get the magnitude of FR. So the magnitude of FR is going to be equal to, and I forgot the little hat there, magnitude of FR is going to be 621 newtons. And again, this is our final answer, so let's put a nice box around it. Alrighty, so finally, we're going to want to find the coordinate direction angles. And again, this is easy. Let's find another fun color. I'm not sure how much fun this is, but we'll find out. Cosine, oh yeah, this one's fun. Cosine of alpha is going to be equal to fx, so the x component, divided by the total magnitude of f. So if we look here, we can tell that alpha can be equal to the inverse cosine, -1, of fx, so the x component, which we know is the 318.7. So I'm just going to go up here and highlight it. That's the x component, 318.7. That's divided by the total magnitude, which is the 621. What happens is we get alpha is equal to 59.1 degrees. 0.1 degrees. So again, this is less than 90 degrees. So this will be a positive value, which again, the 318.7 is positive. It's just a little check. We're good to go. Similarly, we can go beta is equal to inverse cosine, the -1. We want the y component, which in this case is 101.6. So we're just going to go 101.6 divided by the magnitude, which is the 621. And that is equal to 80.6 degrees. 80.6 degrees. I'm actually really digging this color. This one's nice. Use this in future videos. Get used to it. Alright, cosine, -1. And we're going to want the final component, which is the z component, which is -552.6. So let's not forget the negative 552.6. And that's all divided by 621. So this is negative, so right off the bat we know that our angle should be above 90 degrees, and sure enough it is. It's 147.4 degrees. Perfect. So I'm just going to do this. Ooh, looks bad. Alright, let's try again. Try again. Here we go. Round 2. And I am victorious. Alright. So finally, we can go, we've got to state our answers. Alpha is equal to 59.1 degrees. We've got our beta. It's equal to 80.6 degrees. And finally, our gamma is going to be 147.4 degrees. And we're going to show a nice box just to show. Yeah, nice box. All right, jeez. All right, come on, work with me. Don't want to look like a fool. All right, good enough. Perfect. So we boxed our final answers. We're good to go. So just a quick recap. What we did is we found each of the forces in Cartesian vector form using position vectors and unit vectors. It's a very good skill to have because when we get into something called moments, you're going to need to know these position vectors like the back of your hand. And then we simply added the vectors together. You guys have had lots of practice. And then finally, we can just take the components of the resultant vector to find both its magnitude and coordinate angles. Alrighty, so I think that the next two examples are just going to be more practice of this. I'm not going to dive into new concepts. I want to really make sure that you guys have this locked down because I cannot stress how important this is for future work in Engine 130. You guys will learn to hate it, but it's okay because I hate it too, but we'll get through it together. Alright, thank you so much guys, and I'll see you in the next video.